Hello, everyone, and welcome. My name is Barry Vogel, and I'm from Alti. And with me today is Mr. Neil Shaw from Menlo Scientific. And what's your name again? Oh, Mike Klasko, also from Menlo Scientific. And they have a great presentation for you today about anechoic chambers. And I am going to turn it over to Neil right now.
Okay, well, let me share my screen here and share it and then start the presentation. All right. Hi, my name's Neil Shaw, and I'm from Menlo Scientific Acoustics in Topanga, California. My partner, Michael Klasko, most of you know, he's in the Bay Area in Northern California. He has something to do with loudspeakers, I understand. Anyway, a while back, Mark Beach discussed anechoic chambers in an Alti Audio Grounds talk. This talk provides information from the acoustic design point of view and more in the planning for and implementation of walk-in chambers. From my work with some 80 hertz and 160 hertz chambers, as well as random related thoughts. By the way, I'm going to be reading some of this and doing some of it impromptu. We'll look at some of the physical, acoustical, electrical, and other aspects affecting acoustic anechoic chambers. Right now, many people use other techniques to measure some loudspeaker parameters using gatings, etc. For example, the Klippel technique. For some measurements, you need a controlled environment, though, especially for distortion and self-noise. So anechoic chambers are not obsolete. If you have any questions, please use the chat window and Mike Klasko will break in as needed, or we'll deal with them at the end. Anechoic chambers where the lower working frequency is 160 hertz or below are undertakings that meet the criteria for nitroglycerin. Know what you're doing before you do it. This is even more appropriate when people will be in the chamber during tests. With that said, there are at least 7 questions that need to be addressed, whether for journalism, for police investigations, for marketing, and yes, even for research and development projects. Some are more important than others. However, for me, I have to tell you, when I have my acoustician hat on, I know that all buildings are there for the acoustics, so get out of the way. We're going to be going through an overview. We're going to look at the who, what, when, where, why, and how. We'll look at criteria, testing, access and fixtures, space planning, isolation, more, and yet even more. The 7 questions are what, why, who, when, where, how much, and more. And why more? There's always more. You know the story. The first 90% of the project takes 90% of the time, and the last 10% of the project takes the other 90% of the time. It's good to keep that in mind. The 7+ questions can lead to answers to many, but unfortunately not all things. Some may have quantitative answers, or just something driving the project. Others may need to be accommodated or provided for as best as can be. Ideally, these should be addressed and answered before the design and construction, and should be asked way back during the criteria and programming phase of the project, maybe even before that. And let me turn my annotator on. Okay, so the first thing is, why are we doing this? There may be a business case for this. Sometimes there isn't. It's just being driven by other factors. What do we want to do with the space? Programming, size, noise. These are things that need to be considered when you're thinking about the what. Who will use the space? Single user, multiple users, internal or external entities. With a single user, there's a lot less problems. With multiple users, even within the same company, scheduling can become a problem. And when you have external entities, I just think about when I used to do live sound. Somehow the only equipment that broke was mine. So when you have people coming from the outside, they may not have the care and consideration for your stuff that you do. When is this needed? It always seems that you need it yesterday and they want to build it tomorrow. How is the space to be used? This is something that unfortunately is not fully thought out. The criteria doesn't just need to include what you're thinking of doing now, but where those things can lead you to and things that you don't know. And if I could quote a vice president from the past, the unknown unknowns. Now, where is the space located? Space planning. Space planning is the cheapest acoustics you can have. You know, you'll hear me talk about not placing a diamond cutter next to the ore crusher. How much? This needs to be asked from the programming, criteria development, and design phases and closely tracked during construction. And we all know that the engineer's estimate is the cost of construction in heaven. So keep that in mind when you're putting your estimates together. And the more, well, what necessary services and amenities do you need? And we'll get into that a little more. From the acoustic standpoint, the working floor area, the effective working volume to accommodate the device under test, the low frequency cutoff, which defines the effective wedge depth, which in turn defines the lowest frequency for anechoicness, more on this in a bit, and the overall chamber size, which you have to take into account the wedge, the airspace between the wedge and the panel, the mounting of it, the enclosure wall dimensions to find the overall space for the anechoic chamber. Do not forget the outer box, an important safety tip, important safety tip. It would be best if the finished chamber and outer box, if needed, fit in the space proposed by management. Also, in most cases for audio, the noise floor in the chamber is important. So a box-in-a-box construction is commonly used to mitigate any external noise. Now, don't forget, the greater the distance between the inner wall of the outer box and the outer wall of the chamber, the better the low frequency isolation, which in turn increases the overall space needed. The overall height of the base building, where the chamber is built, is important. Will there be enough space between the building ceiling and the top of the chamber to install the fire sprinkler system, which a lot of people forget, and a center structural beam or beams, and the HVAC silencers, which might need to be mounted there. As will be seen later, in some projects, the silencers are mounted to the chamber sides. Now, first thing we want to talk about the size. That depends on the device under test. But as a good rule of thumb, you want the chamber volume, the working volume, to be about 20 times the volume of the object. Sometimes you need more. What's the cutoff frequency? Now that's going to depend on the standard, the research parameters, and more. But basically the wedge depth D is about equal to the wavelength divided by 4. So for a quote unquote 80 hertz chamber, D is about 42 inches. Don't forget, lambda equals the speed of sound divided by F. And C depends on temperature, gravity, especially in California, and the gas constant. And the excess attenuation in air depends on the humidity. HVAC, do you need it? Yes, due to the temperature and humidity. Space planning, most cost effective when done before the space is selected. And some of the amenities or coordination of the load in and load out. And I'll show you some instances where that was limited, the electrical requirements, and more. Now, we mentioned the low frequency cutoff determines the wedge depth. The wavelength is dependent on the speed of sound, which is proportional to the temperature. And the air absorption in the chamber is a function of the relative humidity. At high frequencies, this excess attenuation can become a factor. A good reason to have the temperature and humidity controlled via the HVAC system. Now, for an ideal gas, that's a diatomic gas, the speed of sound is the square root of gamma, the adiabatic index, which is about 1.4. R, the molar gas constant, about 8.3 joules per degrees Kelvin mole. And T, the absolute temperature in degrees Kelvin. And a lot of people don't worry about the air absorption, but they could. If anyone has been to the chambers at Capitol Records under the parking lot, they keep them as close to 100% humidity they can, because there's a minimum of air absorption at 100% humidity. It's impossible to keep it at 0%, and a lot of buildings try and keep it between 40 and 60%. An aside, Vern Knudsen, when he was investigating reverberation chambers at the University of California Southern Branch, there hereinafter called UCLA, was wondering why his numbers were off when he was doing the calculations. And by that means he investigated and found that the relative humidity affects the absorption. Now, is a hemi-anechoic or full anechoic chamber needed? Some loudspeaker measurements can be done in one, while others cannot. For instance, do you need to use a hemi-anechoic chamber due to a factor other than the acoustical criteria? In this chamber, we needed a solid floor because of the weight of the device under test and the various requirements of moving the device under test in and out. What are you measuring? Many ISO and other standards specify a hemi-anechoic chamber. Some internal documents require a hemi-anechoic chamber. Now, some loudspeaker measurements can be done in one, while others cannot. I'll repeat the nitroglycerin warning. Know what you're doing before you do it. More than that, know what you want to do before you do it. In this case, who knows what they were measuring? Were they measuring the noise of the snowmobile, or they were measuring the loudspeaker system in the snowmobile? Now also note here, they had some other amenities. This could be fluid or gas. If you have an engine in there, you'll need to have air conditioning or HVAC bringing it out. Notice the door behind here. We see that there's a fire alarm, lighting, and sprinklers. What is the size of the room and that of the equipment to be tested? What are the minimum length, width, and height requirements of the room and equipment to be tested? Ventilation. What volume of air in CFM is required for testing and to keep the temperature and humidity constant? Don't forget the heat dissipation of the DUT, and especially if there are humans in the chamber, because they give off a lot of humidity. What is the electrical and electronic equipment to be used? What kind of power does the electrical equipment use, and how much power does it need, as well as the power for the control room measurement equipment? When lighting is required, for situations where there are live subjects, including humans, what is the minimum light level of wattage needed for the test? What about noise from the light fixture? You can always turn off the lights unless there are human subjects, and in any case, you're going to need an exit sign. The number and size of doors, and very, very rarely windows, this is very important. These can cause a variation in the uniformity in the anechoic volume, which can affect your test setups. Ambient noise level. What is or will be the ambient noise surrounding the test chamber? Best to know it in at least 1/3 octave band wide, unweighted, or dBz levels, as well as the overall level in dBA. Are there any tones in the noise? Again, what is a low frequency cutoff? What fixtures are needed? IEC baffles? Do you need a chain motor? Fire protection equipment. What do the local codes require? Wet, dry halon? And more importantly, what happens when it goes off? CCTV camera system, access control, smoke and fire detectors, all of these things need to be considered before you start building. Now, can the cable floor support the device under test? Note the stanchions under this device under test. Although there is usually a fine transonded cloth below the cable floor to catch smallest objects that are commonly used to test gravity, a drop cloth is recommended when assembling the fixture. Also, a grabber magnet tool that fits through the cable floor mesh will be needed. Notice here, this is a large assembly that even with the size of the doors we'll see in a moment, could not fit through there, so they needed to be assembled in situ. Can you get the fixture or pieces thereof into the chamber? This one was assembled in the chambers. Note that doors can be a sound leak. You have the doors and the perimeter around there. The best seals cannot usually match the transmission loss of the door panel itself. Now, note where this loudspeaker is located. This may be a measurement test location, but it looks like the location for compliance of testing per ISO 26101:2017, where you measure the fall off in sound as you move away from the loudspeaker. And this is how you qualify your chamber for the anechoic volume. Now, the setup can affect your measurement. Here, the device under test is in a corner, and the measurement is in the opposite corner. Once again, you should know how the test setup can affect the measurements. And here you can see where the door is. And you can see how the anechoic wedges are not in the same pattern as the rest of the chamber. We mentioned the setup can affect the measurement. For example, how does placing the sound source in a corner affect the measurement? Can you always place the DUT in the best working portion of the anechoic volume? This requirement can affect the required anechoic working volume and thus the overall size of the chamber enclosure. But remember, it needs to fit where it is to be built. Oops, the ceiling's too low. Will live subjects, including humans, be in the room? If so, there are a whole lot of codes to deal with: egress, alarms, HVAC, and more. And just wait for the fire marshal and building department to let you know more about the more. Even without live subjects, including humans, some HVAC system is needed to circulate in the chamber to keep the air at a relative humidity level that will not promote the growth of molds and other things. Now we'll get into some examples. Here's a 160 hertz chamber that was placed in a large warehouse space near some other research spaces down here at the bottom. We were able to place it on grade and still accommodate the outer enclosure. But we needed to cut the slab and pour a large mass slab, at least equal to 10 times the chamber weight, due to the vibrations from non-audio equipment in the audio labs. They had some robots in there that were firmly attached to the floor. Now note the door swing, okay? If the control space could have been larger, we could have moved the door a little more to the center and had a full swing, okay? Now the platform at the top of the stairs just meets code, and you'll note that loading is only via the stairs because the control space prevents the use of a forklift to bring equipment in. Now, you have to understand that the chamber outer door swing is impaired by this fortune teller room 1062 and the control room space. Space planning, space planning. Did I mention space planning? Mike, did I mention space planning? Try not to put the ore crusher, in this case, a listing lab where they wanted to have very high levels of audio, next to the diamond cutter, the anechoic chamber, where in this room, when the HVAC was on, the criteria was NC10. Now note the stairs down to the anechoic chamber control space. Load in again is only via stairs. This space was chosen, and then when they found that they needed to cut a pit here and put stairs in to accommodate everything with the existing ceiling height, got exciting. Now, this is a large chamber surrounded mostly by unimproved space at the time. The big problem here was the parking lot to the left. It had speed bumps, and when tractor trailer trucks crossed the bumps, the vibrations were sensible in the location where the chamber is located. So in addition to needing to excavate a pit, the bottom of the pit was a separate slab, and just to be safe, we used 2-inch deflection springs for the chamber isolation. In other words, we wanted belts, suspenders, and super glue because fixing it after the fact won't and can't happen. Now, in that situation where we had the listening room next to the anechoic chamber, this is where space planning is what it is, but money was able to solve the problem of the ore crusher, diamond cutter adjacency. Both the listening room and anechoic chamber were vibration isolated, were box in a box. By the way, the local Quiet Rock rep was very happy with the level of mitigation needed. I think this was the largest order for Quiet Rock they had up to that time. For many projects where an outer box is needed to meet low ambient noise in the chamber, the typical anechoic chamber panelized wall can be STC 52 or so, which is not enough to meet NC 15, let alone even lower ambient noise requirements. Placing the chamber in an outer box can provide much better sound isolation, but care in the high sound isolation assembly construction is paramount, or the money will not be well spent. The higher the design transmission loss needed, the more care is needed. For a mediocre assembly, such as this STC 50, such as that required for many multifamily residence projects, a leak 1/100% of the surface area could cause a loss of 3 points in the measured STC. For higher STCs, an even smaller leak can be more deleterious. More on acoustic noise, both acoustic and electronic, later. Another thing, make sure it will fit and can be built before you lease it or build it. Remember the stairs to the control room some slides back? We needed to dig the hole and depress the chamber, and to a lesser extent the control room. And don't forget equipment on the anechoic chamber roof or sidewalls, like HVAC sprinklers that need to be installed. 2 feet 10 inches can be tight for someone to get in there to actually install the equipment. Now, as noted before, the air between the partitions acts like a spring. The greater the distance between the walls, that is the distance between the chamber and the outer box, the smaller the spring constant of the air, which improves the low frequency isolation. Vibration isolation is always a good idea to decrease vibration noise by the noise that can be generated by the chamber floor. In this case, there were 2 nearby highways to contend with. A site survey to determine the expected low frequency noise generated from the floor is a good idea. It's cheaper and easier than fixing it after the fact, which means it won't. Now, here we see the pit, and we see the access to the chamber comes here. I notice there's a break between this outside wall and here. Now, the overall wedge size needs to be considered. When you have space planning restrictions and noise floor criteria to meet, a foot here or there for the overall chamber, the outer box dimensions, as well as the required airspace can have implications. Most chambers also have some air between the wedges and the enclosure for wedge mounting. Don't forget this. The earlier the coordination with the chamber manufacturer, the better. Once again, let the real estate department know what you need in terms of overall growth space and adjacent properties and spaces. Don't let them situate you next to a cement plant. One client leased 3 different buildings before realizing the volume they needed was not available in the areas they were leasing. Another leased a building next to a rail line, which we were able to mitigate. Again, money can solve many, but not all problems. The cheapest acoustics is proper space planning. Now, depending on your manufacturer, you're going to have different wedge designs, and all of them have some more airspace between the base of the wedge and the chamber to accommodate the mounting of the wedge. We always need to remember the HVAC. Here, the chamber is in a larger space. When you have an outer box, the clearances can be tight. Coordination with the base building mechanical engineer is best before they get into the mechanical system design development, or DD phase. When this is done during the construction or CD phase, it may be too late. Your acoustical consultant can determine the maximum noise from the building HVAC at the connection to the chamber silences. Okay, and it's important that you pass this on to the mechanical designer. Now, the acoustical consultant usually have this can have this ready quite early in the design process if the ambient noise requirements of the testing protocols proposed for the chamber and the silencers to be used. In many cases, the chamber manufacturer will also supply the silencers. There's lots of room here. This is not always the case, especially when in an existing multi-story building. P.S. It's best to place the chamber on grade, not on upper floors. Now, this chamber is in a large space where there are other activities. For this project, a single chamber wall is sufficient to meet the chamber ambient noise requirements, but they're locked into that. And so, in situations like this, the noise break into the duct system needs to be considered. Normally, the mechanical engineer will specify 24 or 25 gauge metal. For their duct work, 20 gauge might be better. As noted before, it's always a good idea to let the building HVAC mechanical engineer know the noise level at the connection to the chamber silences. Note, this chamber silencer extends quite a bit from the chamber to where it meets the building HVAC. This may be due to the fact that they needed the extra length to attenuate the noise from the system, or it may have been because things were going on up here where they were not able to accommodate the silencer up here. Note the structural beams. You can't get ductwork through a structural beam. Coordination is important. Now, this is the return air silencer, which emptied into the void between the chamber and the outer box. This would have been interesting if it was a supply air silencer, because here's the conduit for a light in the chamber. Now here, you can see the hole for the sprinkler here and where the sprinkler was going to drop down. There's always a resilient or a flexible coupling between building services and the chamber itself. Now you notice there's a lot of debris up here. Debris can cause noise when vibrated by low frequency noise in the chamber. Remember, STC52 panels do not have good low frequency isolation, and that could be very, very difficult to fix if the access is limited. Now, many chambers require sprinklers. So note the flex connection to the chamber and the roof mounted sprinklers. The penetration through the roof for the sprinklers and lighting needs coordination, as these services are usually installed by subcontractors other than the chamber manufacturer's installer. Flexible connections are also needed for electrical and low voltage connections and other services, device air, device fuel, etc. if needed. Also note the ceiling structural beam. This can cause problems when HVAC is run perpendicular to the beam in low clearance situations. Can the length of the silencer fit? Now, this yellow rope was removed when the construction was done. I made sure of it. Here are a lot of electrical and low voltage connections for one chamber. Note the sprinkler loop down below in black and orange. There are quite a few conduits here. Local codes may require electrical and electronic cables for different systems and with different voltages to be segregated. In some instances, only the lighting, fire alarm, and security connections are needed, and pass-throughs between the chamber and the control room are used to provide a path for DUT power and measurement cables. Note, some labs, and my recommendation is that the DUT and control room equipment be served by the same panel board. More on this in a minute, and the panel board located in the control area, so you don't need to go hunting for it if you inadvertently pop a breaker. Now, are you measuring a snowmobile or a loudspeaker or a consumer product? For the latter two, being able to see the self-noise of the device is important. As Mike Klasko says, which has less self-noise, a silk dome or an aluminum dome? And one way of determining the self-noise is using multi-tone testing, which Dean Jensen and Gary Sokolach talked about 35 years ago. Now here's a multi-tone signal where the tone peaks represent the frequency response, and the dirt between the tones is the noise. A quiet background lets you see more of the dirt between the tones, and thus compare changes to the device and hard parts when you're in development. One change at a time is better to see the more cost-effective change.
Let me interject in terms of self-noise. Imagine waving a silk scarf, which would be silent, versus a sheet of aluminum. And that tells you this is what you're looking for those stress noises in the material, the internal dampening.
Yeah, and for example, let's say you change the cone material. How does the cone breakup change, and does that lower the noise? For a loudspeaker, the choice for the multi-tone testing tones include the number of tones, the frequency for the tones, the amplitude for each tone, and the phase for each tone. The tone, frequency, amplitude, and phase is important, especially the frequency selection, so any harmonics or intermodulation products are not hidden by a tone. Now, if we're looking for the dirt between the tones, we need an acoustic environment that is quiet, but what is often overlooked, the electrical and electronic noise needs to be even lower. Make sure the measurement equipment noise floor is substantially lower than the acoustic noise floor, and the acoustic noise floor is lower than the device under test noise. Here's the published 1/3 octave band noise for the B&K 4189 connected to a 2250 sound analyzer. Over here we see that at the low end, the noise is dominated by the electrical noise, and at the high end it's dominated by the microphone self noise. Now for some devices, the electrical power noise can be important. This can be a factor when the DUT power supply rejection ratio is not sufficient to reject the noise in the electrical power. In some cases, say 150 hertz, the low frequency ambient noise is less than 10 dB below the output of the DUT. This means that you should always measure the ambient noise before and after a test, so you know where to draw the line in the low frequency response to the DUT. You don't want to be measuring the ambient noise. You want to measure your device under test noise. Now let's just look at two 1/2 inch measurement microphones. The graph shows a good general purpose microphone, the B&K 4189, connected to a ZC0032 microphone preamp, and a low noise microphone, the B&K 4199, with a laser welded preamplifier, both connected to a popular type 1 sound isolator, either 2250 or 2270. Compared to the ISO, minimum audio field, the dashed green line, and some noise criteria curves, the dotted lines. Noise criteria is sometimes used to describe the noise level for a space and is a common metric for mechanical system noise. The 41, 89, 22, 50s self noise, the solid blue curve, is 17 dBA. The 49, 55, 22, 50 self noise is 4 dBA, the solid red curve. Note the 1/3 octave NC curves below NC 15 are extrapolated. The overall A-weighted sound level for noise that follows these curves from 63 to 8,000 hertz is 15 dBA for NC0, 19, for NC0, and then here 19 dBA for NC5 and 23 dBA for NC10. These are important to know when you're designing your chamber to make sure that you can meet these criteria and what they actually mean. By the way, PCB, D, AS, B, and K, among others, make some mics with even lower noise floors. In many projects, the electrical power distribution is large and has many parts. These parts serve everything from rotating equipment like chillers and other HVAC equipment, kitchen equipment, lighting, convenience power, IT servers, and more. So you can see in this situation, we had a large existing plant and we added what we needed for our situation. And you can see that off our panel, we had other panels there. And so we had to intersperse a isolation transformer there. And just for example, in an existing plant, you should take a look at the power quality, because you can see here that there's a lot of problems with this power here, and we have a lot of harmonics, which can wreak havoc if the power supply can't handle the rejection of them. So this goes back to what is the criteria? What is nearby? How is the power distributed? For this facility, where we had the ore crusher next to the diamond cutter, we had two sources of power, clean and very clean. We had isolated ground and we had clean. You'll notice here on the chamber, there's no power or other services in there. Anything that was needed for measurement or power was brought through a pass-through. And over here is where the panel board was. So we had control over the circuit breakers and didn't have to go hunting elsewhere in the facility. There was an isolation transformer mounted right here. We were lucky in that the electrical room was located over here. I don't know if to say lucky, but fortunate. Now here's an example of the drawing as prepared by the electrical engineer. We have the existing switchboard coming through our two separate transformers, one with the harmonic suppression and one just, well, they're actually both here. And these go through circuit breaker boards to our, from this low voltage switchgear to our panel boards. This is what we wanted. We wanted to have the harmonies, and then we wanted to have an isolation transformer. The shop drawing enabled us to fix this. They opted not to put these in, but at least they had their provision for it, which is very important. You need to look at shop drawings, not just for the electrical, but for everything. An observation during construction that where they say similar is just that. And that all the transformer and conduit vibration isolations are installed and installed correctly. Thanks for joining. Any questions? Yeah, let me stop my screen share. There we go.
Well, one question, Neil, is what is the minimum dimensions required for a room to build an anechoic chamber where a speaker will be measured down to 20 hertz? Let me also say that maybe the question is, how can somebody do a hack or out-of-the-box solution to extend the low end response given fixed dimensions and whatnot. And then finally, let me throw in two other thoughts for you. One is Don Keel's idea that the walls should not be solid, but maybe a limp mass for the fiberglass, and can that kick up the low end response? And even techniques such as metamaterials, where the speed of sound is very different.
Okay. Let me answer the metamaterials right now. Find me a project where they have a budget for that. I'll be glad to use them. Okay. In regards to Don Keel's suggestion, that's very good, except you give up the sound isolation when you go to that damp material.
I think he was thinking you build the solid box and then maybe hang the fiberglass as a limp mass using a sort of reactive solution. I mean, again, you don't want a bent ruler for a measurement chamber and you want to follow the textbook, but this was just a thought of kicking up the low end in a compromise installation.
I think that's a great idea, but I would find it hard to locate a contractor who could implement it properly. You know, the devil's in the details there. And now when you talked about how do we get an extra, let's say 1/3 or half octave more anechoicness out of a chamber that's, let's say, designed for, well, let's say money and space won't let you build what you want. Well, there are many techniques to do that. You can use gating in there. You can use, I just forgot the other one.
Well, a near field solution where you do a separate measurement and then splice it on and have the microphone a tiny fraction of an inch from the cone, where the sound energy from the speaker diaphragm dominates what's going on in the room, and the noise in any sort of noise in the room where the isolation isn't good at below some frequency. But of course, then you're back to splicing, you know.
That's a common technique for measurements in a real space that's not anechoic. All right.
Yeah.
Now we have one Q&A I see from an anonymous attendee. And it sounds like we just answered that question.
Yeah.
Okay, there's a lot of chat going on. Oh, let's go up to the first one. Charlie Yu says hi. Dennis from Denmark is listening along. Caroline Nagy says, hi, Mike. In my car. Wear your seatbelt. Steve Garrett. By the way, his second edition of his book, Understanding Acoustics, is out and it's open access. If you need the link to it, just go to Springer and you can find it there. Okay. Chamber cutoff isn't a brick wall, so often, Scott Holden says, so often you can get results below that frequency. Yes, you can, but make sure you know what you're doing before you do it. You know, there's a song by Bonnie Raitt, Fool Yourself. And we're all very good at that. So Barry, anything else?
No, I've learned some interesting things about anechoic chambers that I certainly didn't know, and I've attended several of these presentations. So this was really good information, and I wanted to thank everyone for attending. I want to thank Neil and Mike for doing this, and let everybody know that a link to view this will be available by tomorrow on the ALTI website. That's ALTI. ASSOC.org, and anyone can download it. It's open source.
Great. Thank you all for joining.
Thank you, everyone. Have a great day.
Bye-bye.
Bye-bye.